Well, everybody's seen Contact, um, and Jodie Foster, when she was being sent up in the wormhole to meet the aliens, got a nice picture of a galaxy in there, and she made a statement that they should have sent up a poet. Well, our next speaker, when I asked him to give me a short bio to introduce him, sent me a poem. So I think he's after the Jodie Foster poet slot in SARA. So here's the poem he sent me. While still a lad, he climbed high trees and watched the ways of bees. Soon he was scaling rocky peaks and hanging out with geeks. Retired in a peaceful place, he now explores deep space, seeking radio waves from stars, the music of the spheres. With that, welcome Dan Layne. Go ahead, Dan.
All right. Yeah, thanks. Good job reading that. Just a quick sound check. Do I sound okay?
Yes.
All right. And so you should be seeing my screen now. So yeah, I'm going to be just a very narrow focus, just talking about some algorithms for pulsar detection. I'm with the Deep Space Exploration Society in Colorado, and yeah, we do have access to a 60-foot dish in southeastern Colorado, which is great to use, but it's a long ways away. It's a long drive down there, and so we have to make the most of every opportunity. And I also want to thank the whole team. There's been a lot of people working on this, refurbishing this dish over the years to get it to work, and I've just shown up lately and just having fun collecting data and processing it. So I'll be talking about that. Slide 2 is just kind of the outline. I want to talk about some of the observational properties of pulsars. The two algorithms I'll be comparing are one in the frequency domain, which is Presto, and the new one in the time domain is called Riptide. And this is an empirical evaluation. I'm not going to get too much into the theory of the algorithms, just comparing data. So to start with, just some observational properties of pulsars. You've seen some of these basics before. Pulsars are highly magnetized, rapidly rotating neutron stars formed from the collapse of a supernova explosion. They emit a broadband beam of electromagnetic radiation from the poles, the magnetic pole, and the pulse is observed when the beam points toward Earth. You know, yesterday Wolfgang mentioned about the steep learning curve. Well, I think I'm at the bottom of that steep learning curve. There's gaps in my knowledge. There's a lot to learn. It's just fascinating, everything that we can do with this hobby. And I know, you know, Wolfgang mentioned that, you know, it's all about physics. And so I do go read some of the physics papers and scratch my head because, you know, they're talking about these spinning neutron stars, and the papers make my head spin because oftentimes they end up saying, well, we don't fully understand what's going on here. So this is still, pulsars are new enough. The models are not complete. The theories are still being developed. So it's fun to be on the fringe of this. Observables here include the period of the pulse, the period derivative, which is the rate of change, and the profile. Pulse timing is very consistent. They make great clocks. The period of a pulse can range from, some pulsars are down to just a few milliseconds. Others are as slow as dozens of seconds. But the pulse intensity and shape can vary widely, and that can be due to the propagation through the interstellar medium. We'll talk a little bit about dispersion. Scintillation is the multipath interference through the plasma, and then the Doppler shift, the motion of us. You know, the Earth is moving. So those are some factors. I'll start with this example, a beautiful example. This is from the Parkes 64-meter dish in Australia. I have visited Australia, but I'm not a citizen, but they make their science data freely available. And I think the scientist reserves rights for 18 months, and then the data is freely available. So I was poking around there and found some of their 1-bit analog filter bank data that the Park's 64 meter used. I think they discovered hundreds of new pulsars with it. In this case, this is Vela. Just a beautiful example of very clean data with a very strong pulse. You can see the pulse. The pulse period is down here. It's about 0.9 seconds. And so you can see about every 9/10 of a second, the pulse is repeating. It's very clean, very strong. This is the brightest pulsar. In this case, I downloaded the raw PSR fits filter bank data from Parks. And then I used some Presto tools to generate a time series. And this is just with their tool Explore that. And one reason I'm using data from somewhere like Parks is I'm trying to learn these algorithms and compare these algorithms. And so there's the factor of the algorithm, there's the factor of the data. Do you have clean data, noisy data? And then there's the factor of myself, the operator. So I'm trying to eliminate as many unknowns as I can. So I do have some samples of really good data so that I can understand the characteristics of the algorithm. So this is pristine data. This is the best you'd ever get. This is what we typically get down there at Haswell with the Plishner 60-foot dish. And this is probably what you see also if you're looking for pulsars. In this case, it's B0835-41. This was a collection I did just in June of this year. So this is a much weaker pulsar. It has a period of 3/4 of a second, but it's really hard to look in here and see if there's any pulse repeating every 3/4 of a second. So this is typically what we see. And what we have to deal with is trying to integrate enough data to pull a pulse out of that. So yesterday, Wolfgang mentioned dispersion. Here's another illustration of it. The higher frequencies are detected slightly earlier than the lower frequencies, just due to the dispersion by the electrons through the interstellar medium. So this is the uncorrected delay. And then up here on the top is a pulse that's been dedispersed and integrated. The dispersion measure that we use is proportional to the density of electrons along the line of sight. So there's a column of electrons between us and the pulsar, and that's represented by the dispersion measure. When I first started this, I naively thought that the dispersion measure was also related to the distance. Well, it can be, but it certainly depends on the look direction. If you're looking down through the Milky Way towards Sagittarius, towards the center of the galaxy, then the dispersion measure is much higher than the real distance. If you're looking perpendicular to the plane of the Milky Way, looking out towards Andromeda, for example, then your distance will be much higher than the corresponding dispersion measure. Anyway, this little equation corrects the delay. It's just delta t is 8.3 times the dispersion measure times the bandwidth divided by the frequency cubed. So in this case, the units are microseconds for the delta t. The dispersion measure has these odd units of parsec per cubic centimeter, and the bandwidth is measured in megahertz, and nu, the frequency, is in gigahertz. So there's kind of two main factors I'll be talking about throughout, and one is dispersion, and the other is folding. You've probably seen this cartoon before where there's a weak pulsar hidden in this noise somewhere. And basically we fold, if it's a paper strip, we fold it at the desired period. It's either known, or if you're searching for an unknown pulsar, then you do a search trial until you find it. You add them all up. So we're basically integrating or adding up all the small contributions until we get a pulse appearing. This folding can be performed in either the frequency domain or in the time domain. And when we can, we like to use the professional algorithms. They're designed for pulsars to search for new unknown pulsars. but we can take the tools and to detect known pulsars by constraining the search parameters. So instead of doing a blind search, we just say, no, we already know what the period is. We know what the dispersion measure is. We know what the factors are of this pulsar. We're simply trying to find it. We know which direction it is. We're trying to detect it. In the frequency domain, the basic algorithm is called the incoherent harmonic summing. It uses the fast Fourier transform. The main tool is Presto, which has discovered lots of new pulsars, and it uses tempo in the background for timing. There's another tool, a newer one called PS Archive, which uses tempo too. I'll not be talking about that. I do want to note that Presto can also process time series data. So Presto is a large package of lots of tools. So besides just doing the pulsar detection, it has other capabilities. It can do time series, but it's not its strength, and it's my experience is they're not as good. And so I won't be talking about the Presto time series capability here. When I say Presto, I'm talking about its frequency domain. In the time domain, there's a phase coherent search technique for the periodic signals. Basically, you're looking for a periodic signal with the highest SNR, the signal to noise ratio. And the fast folding algorithm has been around a long time. It was first described by Layne in 1969. The version I'm using here is called Riptide. It's a recent Python C implementation. It's available on GitHub. And this is the main paper by Morello and others from August of 2020. They go into great detail of describing their implementation of the FFA and what advantages it offers. The reason the fast folding algorithm is getting more interest now is because, at least in the case of Riptide, it makes very efficient use of the CPU cache. So modern caches can enable algorithms to run faster. And so for a long time, FFT methods dominated because they were faster, simply because of the CPUs that were available. The CPUs that are available today are much faster and with better caches. So there's no longer a speed advantage to using the FFT. I do want to make a note that the Riptide FFA only does folding. It needs an external dedispersion tool, and that's because it was developed for a professional observatory where they have a data pipeline, and in that data pipeline, the raw data is already dedispersed. So dedispersed data is readily available in their pipeline. And so that is something to consider. We need the external dedispersion. The Riptide period search process does a depth first, divide and conquer folding transform. So originally, the original algorithm by Layne did a breadth first. They have found using the cache, it's easier to, or better to do a depth first transform. And it uses a matched filter. The matched filter is a boxcar, also called a top hat, to find Gaussian peaks. Well, pulse profiles can be modeled by a Gaussian peak. So a Gaussian can model almost any of the pulsar profiles we have. Sometimes you need more than one Gaussian. You might need multiple Gaussians for a complex pulse, but Gaussians work great. And a boxcar is a very quick way to find Gaussians. So basically, we're doing a match filter for Gaussians. And what the Riptide does is returns the highest signal to noise ratio per period trial and per pulse width trial. So not only are they varying the time of the folding, they're also varying the width of the boxcar narrow to wide to get the best peak there. And when I say it's improved sensitivity, that's improved sensitivity over Presto, especially for narrow pulses in the presence of RFI or low frequency noise. That got my attention because although in Haswell, a very remote location, we don't have much RFI. We do have our share of red noise. We have some low frequency harmonic noise that does make it harder to find the pulsars when they're weak ones. So I'm going to skip this flow chart for now. It's in the paper, they describe it. So back to Parks. I was just fascinated with this one because, again, I wanted some nice data to understand the algorithm. I was looking around there, and several years ago, they did a survey for pulsars in the large and small clouds of Magellan. So LMC is the large Magellanic Cloud. And of course, we can't see the clouds of Magellan from where we are here in Colorado. But if you've been in the Southern Hemisphere, you can see the clouds, the smudges there. And so I just went through and found this one. It was a long collect, many hours. In this case, I'm just using this as an example to show what riptide looks like. And so time goes down on the phase. This is the phase time plot. Time goes down, and here you can see the pulse. I'm showing 1.5 periods of the signal. And so when it changes color here and you get a repetition, that's the next period. So this is 1 period here in the gray. This is the pulsar pulse here. The gaps are due to scintillation, and both plots. So this is the phase plot, and this is the profile plot showing the detected peak. In this case, it has a very high SNR, 59. So it's a very strong signal, a nice clean pulse. And again, this is with the 1-bit analog filter bank data that they converted to PSR fits, and then I'm using here. So this is basically what the plot looks like. I've modified it a little bit just to add in the header information down here. I'm not doing a dispersion, I'm not doing a distance search, so I'm not showing any dispersion measure plots. I just simply print out what value I gave it because I fixed that. I'm not doing a search. So that's the riptide plot. This next plot shows, this is the exact same plot I just showed, but what I'm going to be doing here is comparing that with Presto. So this is the exact same plot we just looked at on the previous chart. In this case, the flux for this very distant pulsar is 0.3 millijansky, so it's not very strong at all. This is the Presto chart here on the left. Last year, Wolfgang gave a great tutorial on how to interpret this. Peter East has also described how to understand and interpret these plots. So I'm not going to spend much time on that other than just, this is the period derivative and the period, a two-dimensional view of that. You want these lined up. Here's the dispersion measure. You want the dispersion measure to be non-zero. Zero dispersion measure means you're looking at something right in your own shack there. This is the phase and frequency plot, and this is the phase time plot. Notice on Presto, time starts at the bottom and goes up. Over here on Riptide, time starts at the top and goes down. So that's a slight difference. Here you see a bunch of noise at the beginning for the first several thousand seconds, some noise. Well, you see the same noise over here on the Riptide plot. You see the same scintillation going on here that you see here. So I run this. The red box here is the detected topocentric period that Presto came up with. And that's the exact same period that I ran it with. And in this case, it's the exact same period that Riptide found. So I give Riptide a bounding box for the period. I don't know the exact period. I just give it a bounding box and tell it go find the highest SNR curves within that bounding box of the time. In this case, down to the nanosecond, Riptide found the exact same period that that Presto has. So using very good data gives me confidence that I'm starting to understand Presto and Riptide, and then I can go evaluate them when the signal to noise ratio goes way down and understand them better. So amateurs operate at lower signal to noise ratio with generally higher RFI than the professionals. We would love to have SNR greater than 10 for robust results. As Wolfgang pointed out yesterday, often, our target SNR is around 5. If we get around 5, we can usually get acceptable results. Peter East has modified Presto to use SNR as a measure instead of what Presto uses is a chi-squared, reduced chi-squared statistic for determining the result, and Peter East has modified it for low SNR, and he's gotten good results with that. I do want to say here in this discussion, I'm going to be talking about 2 different measures of SNR, the time domain SNR and the frequency domain SNR. They both trend up and down the same, but they're not the same measure. So when I say expected, that's the theoretical expected value for the time domain SNR, and I'll just denote it with a sub FFA. It's based on the profile. So it's the total energy in the pulse, the square root of the number of samples divided by the period times the square root of delta is the duty cycle of the pulse. And then in the Fourier domain, the theoretical or expected SNR looks like this. It's, H is the number of harmonics, S is the signal strength, L is this generalized Laguerre polynomial, and the only reason I'm showing this is because I'm using these 2 equations on the next chart to show a comparison. So I did not generate this. This is lifted straight out of the paper by Cameron, where they did a simulation to compare the expected SNR for FFA and FFT at different duty cycles. So here on the left is the SNR for duty cycle of 0.2%, and then this one is 1.0% duty cycle. The dots, the discrete points, are the simulation results. The solid line then being the analytical. The analytical is the equation we had just on the previous page. So it has the equation, the analytical, and the simulation. They agree very well in both cases. And both cases show that theoretically, the fast folding algorithm, the time domain algorithm, will do better than the Fourier method, at least on this range of data. They were interested in data from 2 to 14 seconds. So they're looking at long range pulsars, longer period pulsars. And then this chart on the right simply shows the ratio of the SNR FFA over FFT as a function of the period. Again, just showing for each color is a different duty cycle, just showing for different duty cycle that the FFA method theoretically can be better. And so I also had some data from the Green Bank Observatory. This is actually data I collected last year. So last year I submitted a request on the SARA Skynet account for crab data. I did a 6-minute collection on crab and got the Presto result on there. And then I said, I really want the raw data. Where is it? So Skip Crilley was very helpful. Since he helps there, then he was able to set up an account where he can get through their firewall, get the raw PSR fits data, and he put it in a Dropbox for me. And I think that's what Steve was mentioning earlier today, that the raw Pulsar data for Green Bank is available on the 20 meter. Just get it through this process, because then once I have the data here, then I can play with it myself. In this case, Presto gets very good results. The phase trace is getting fainter here, but you can still see it, very strong pulse. The reason in the frequency plot that there's large gaps here is Green Bank blocks out large gaps of their frequency due to RFI. So they have RFI, they just block out the whole band. So that result looks good. And that SNR was 7.3 in the frequency domain. I ran Riptide on the exact same data, and Riptide looks good. You see the pulse, good profile, SNR 12.9, and the period agrees at least out into the microsecond range. So I thought, well, what if I reduce the SNR, I can reduce the SNR. And actually, the data, the PSR fits files are large. There was actually 6 of them. There's 6 files here for 6 minutes. Each file is roughly 60 seconds. When you run Presto on multiple files, it 0 pads the slight gap in between. So there's a gap of a second or less between each of the collections when they split the file. Presto 0 pads it. You don't even see that there's a gap here. But I thought I'll just run it on the first one and see what happens. So this is running the same algorithms on just one file instead of all 6. So it's 68 seconds of data. SNR was 2.1. Presto fails. There's some hints that there might be a pulsar there, but you can't draw a conclusion. So in this case, I'd say it's inconclusive. Whereas when you go over to Riptide on the same data, the 68 seconds, you can see the phase trace here, and you get a pulse. It's much weaker, 7.8, but I think this is good enough that I'd say, well, yeah, I know there's a pulse there, and that's what I'm trying to figure out. Do I even have a pulse? Presto would leave you with nothing, whereas in this case, Riptide would say, yeah, you have a pulse. It's weak, but it's there. And that's kind of why I'm using this new tool, Riptide, is this often happens with data I collect from Haswell. I say, oh, do I even have a pulsar? I can use Riptide to independently confirm that I have a pulsar and to help screen when I don't. Crab Nebula itself is beautiful. Very nice, pretty picture here. It's from the supernova remnant that was first observed in 1054. The Crab pulsar is actually this red star right here in the center. It's one of the, there's only a handful of pulsars that they have identified an optical counterpart with it. So it's kind of unique. It's close enough they can actually find the neutron star, see the optical counterpart there. The period is 33 milliseconds. Of course, there's polarization in the data, both in the radio and the optical. This image is from the optical is from the Hubble Space Telescope in red, and the blue data is from X-ray bands from the Chanda space satellite. So I'll finally get to what we were doing there with our data in Haswell. This is the 60-foot dish. Everything is on GPS. We have a network time machine there for synchronization. We use Linux, so it's a System 76 Ubuntu 20.04 host. And everything I'll be talking about in here was either collected with a B210 or some of them with the N210 SDR. There was 3 different feed horn configurations. One was at 408 megahertz with this LNA, and the filter was at 90 megahertz. We currently have up to 1296 megahertz feed horn, which is the same feed horn we use for the moon bounce. We do the EME moon bounce contest in the fall, and so it's actually right now that same feed horn. We can detect pulsars with that at those frequencies, and we also have used the 1420. The 1420 we use for hydrogen as well as pulsars and other experiments. On the software side, everything here runs in Linux. Murmur has been mentioned. It's a great tool. It runs under Linux. I use the Wine emulator to run Murmur under Linux. I also use Stellarium to plan the observations. I use the ATNF database from Australia to generate a .par file, which has the ephemeris for the pulse. Or it tells the software exactly what time to be looking for the pulse, and it has the dispersion measure and all the published values. We have our own dish control software for the pointing and tracking. It was done by a group in-house. It's excellent, works very good. And so we set up, we set up a target pulsar, we point to it, start tracking, and then I turn on all the pulsar software. We have a software spectrum analyzer for looking for RFI, a GNU radio filter bank. It originated with Marcus Leach, and then we got ours from Joe Martin, K5SO, that he had simplified it quite a bit. I got it and I simplified it a little bit more, and I converted it to Python 3, so it would run with Ubuntu 20, and I also just put a wrapper around it, so it's all scripted right now. We're using the current version of Presto with Tempo. for pulsar detection, and also using the current version of Riptide. That's available on GitHub. And there's some miscellaneous utilities, SIGPROC and WattUtil and some others. This is the methodology. I collect the data. I've tried RFI masking, but we don't have that much RFI. So RFI masking doesn't make much difference on the data I have. Over on the right, when I run Presto, I run the prep fold command and give it the period and derivative. But then actually I'm using the .par option. So this is all automated and it generates the Presto plot. In the middle, as I said, to run Riptide, it needs a de-dispersed time series. So I use the Presto tool called prep data. Since I have a single subband here, I use prep data, no Berry because we're doing everything in topocentric coordinates. And I give it the dispersion measure. And then I run that resulting time series into Riptide and I get the plots we've been looking at. Riptide will work with either Presto or SIGPROC de-dispersion. So I did also try SIGPROC de-dispersion. It's older, it's slower, and I found that it didn't work as good. SNR would be a little bit higher and sometimes these would be darker. So I really won't spend any time on the SIGPROC version. So I do want to show some comparisons now. This is back to the earlier one where early on I showed an example of 835-41, just some noisy data. And this is what the pulse looks like once we process it through the software. It's actually a nice pulsar, good strong SNR 12.7. You can see all aspects of the Presto plot look good. And Riptide shows a very good strong pulse also in the phase and in the profile. And they have a close agreement on the period. So, starting to run these, I started building up confidence that Riptide works and I'm starting to understand it, as well as Presto. Presto is, there's a lot going on. It takes time to learn Presto. Here's another pulsar. So all the pulsars from here on out are ones we've collected in Haswell. This is J0437-4715. It turns out it's the closest and brightest millisecond pulsar. So its period is 5.75 milliseconds. It's a very fast one. It's the fastest one that we've collected. So Presto did good on it. You can see the various aspects here that Presto is fine. And also the Riptide plot looks good. And mainly I checked to make sure that the periods are both correct. So here's another one, B20, 20 plus 28. Happens to be a double peak pulse. It's called mode changing because there's a double peak and it switches back and forth. And so that's something that the physicists are working on models to understand how the peaks in this, these very intense magnetic fields on these pulsars can generate these, but this is the data we see. Here, the SNR was 4.8. So it's getting down below 5, and yet Presto still shows acceptable results. You can see the phase trace, you can see the pulse profile, the P and P dot. And just as well, Riptide also finds it, and both with very close agreement on the period. It's interesting, and I don't know why, but as you look at the data, for about the first 9,000 seconds, it's hard to see any phase here. At the end, you start seeing the phase trace. Well, the same thing here. We have to go down, for the first 9,000 seconds, not much. And then towards the end, you start seeing the pulse. So that's just how it is with scintillation and how the data is sometimes on pulsars.
On that last one, we had the double peak on the right, but not on the left. Fascinating.
Yeah. Don't know why. So in terms of performance, again, Riptide does folding only. So if we're comparing Riptide with the basic Presto, we have to subtract out the de-dispersion time because Presto will do that on the fly for you. So again, it's hard to compare times. It's like comparing apples and oranges. When you run Presto, you get one candidate plot. Sometimes that's not as good as you want, and so you can iterate to improve the results. You can refine the value of the period, you can change values, you can iterate to improve the results. When you run Riptide, you as the user specify how many candidates you run. I usually say 10. You can do 100, you can do ever how many you want. So you get a bunch of candidate plots back, and they're ordered by SNR. So you need to visually scan the plots, and it doesn't take any longer to scan these plots than it takes to look at the Presto plot. When you look at the Presto plot, you need to look at each part of it and see, well, does it all add up? Here you're just flipping through a bunch of JPEGs real quick, looking for a good plot at the right period. My experience here was for any of our data collections less than an hour, either algorithm ran quickly in under just 1 or 2 seconds. So it really wasn't a factor. We don't have a huge data pipeline. You know, we do the onesie twosie thing, so that didn't matter. I did have 2 longer collections. The 2020 plus 28, the one we just showed on the previous slide, was 3 hours of data at 1 millisecond sample rate. The filter bank, the raw filter bank, was 20 gigabytes. The time series, the dedispersed time series, was 40 megabytes. The time for Presto to do dedispersion was 31 seconds. And then the folding was 6 seconds. So just looking at Presto, you see, oh, most of the time is spent in dedispersion. Folding doesn't take that long. And then when I did the Riptide folding on the same dedispersed file here, it took 12 seconds. So it took longer. This is a very recent collection we did, B0355 plus 54. It was 4 hours of data, much smaller sample rate. The sample rate we vary depending on the Pulsar pulse rate and on the width of the pulse. So we try to set the sample rate to be about 1/10 of the width of the pulse. So the sample rate will vary. Of course, that generates more data. In this case, it was 54 gigabytes. The time series reduced down to 212 megabytes. Presto took a little over 3 minutes to do the dedispersion. Then Presto took 17 seconds to fold, and then Riptide folded in half the time, 9 seconds. So I only have two data points. They don't even agree. One says Riptide is slower, one said Riptide is faster. So don't have enough data points to draw any conclusion other than they're both fast enough for the work that we're doing. I do want to show a few more examples here. B0329 plus 54 is the brightest pulsar in the northern hemisphere, and so that's one we often start with. And down at Haswell, we usually collect it before and after when we do a long pulsar, just to make sure that all of our system is still working. I'm going to show a sequence here. This was using our 1296 feed horn, 10 megahertz bandwidth, and in this case, a 10-minute collection. So Presto SNR 10.8, Riptide, the SNR was 36.6. Again, you can't directly compare the SNRs. They both trend up and down. Both algorithms did fine. And by the way, this plus 54 is also a mode changing pulsar. So you'll see the profile change. So what I did was similar to what I did with the green bank data. I trimmed it down. I cut it in half. No, this is a fourth. So 150 seconds of the same data. SNR down to 2.7. In this case, Presto fails. Presto is not acceptable. You can't draw a conclusion here. Whereas Riptide, you still get a pulse in the profile, and you can see a faint trace here. It's not a strong one, but there's enough there you can see with the eye and say, well, yeah, I think I do have enough data that I could declare a pulse there. So another case where Riptide works, Presto's inconclusive, although the SNR is below 3. And then the last one in this sequence is I trimmed it down to 66 seconds. Both of them fail. So Riptide did produce plots, but I can't see it in the phase. Riptide, when it gets down this low, it's struggling. It's still trying to produce something, but if Riptide doesn't find a curve, it won't produce any plots at all. So when you're running Riptide, if you get nothing back at all, if you told it 10 candidates and you get none, that means it didn't find any curves for the matched, the top car or boxcar matched filters. I'll just show one more of 0329 plus 54. This was another 10-minute collection on the same day as the previous ones. It was just a different collection. Why it worked on 600 seconds before and now it doesn't, that's scintillation. There's really, you can't draw a conclusion here. It has a SNR again below 3. Whereas with Riptide, you can look and see, well, I can see a faint trace in the phase here, and also the strong enough pulse that I could declare it. It does have the correct period. I forgot to mention on like this one up here, another reason, and this is one that I trimmed down, another reason I'd say, even though you can kind of see a pulse, a reason I say that it failed, it's got the wrong period. The period is off by a considerable amount here. The same thing with Presto, both of them, it can't get the right period. So that's something to always check. I'll do a few more. This was 1641-45, a 30-minute collection, good strong results here with Presto. This is the dispersion measure here. Noise like at 4,500 seconds shows up here. Same noise here in the pulse profile. These gaps here on the frequency plot are due to my own learning curve. I had the gain set too high. So this was an early collect I did. I had the gain set too high, so the algorithm just drops that data is washed out. So I have learned to reduce the gain. But in either case, both algorithms did well on this one. Here's another one, 1749-28. Both of them do very well. There was some data missing at the beginning. Same thing here, the data is missing at the beginning. And I think this is the last one I'll show. I've been showing kind of the pipeline view on Riptide. When you go to GitHub and download the Riptide package, you also get a Python notebook package. I use the Jupyter notebook. You can use your own preference, but the notebook is very handy. I used it to learn how to interact with the algorithm. So first I used the notebook to learn how to run it, and then once I got a handle on it, then I just script the run the scripted version, the command line. But with the notebook view, you can go in and interact more. You get a little bit different view on the plots, and you can get a nice pulse profile as well. So again, this was on 20, 21 plus 51. Both of them did fine on that. Now, for those of you using Windows 10 and 11 that might be interested in this, the Riptide is very simple to install. If you have Python 3 installed, you just do pip install riptide-ffa. It installs Riptide. The problem I pointed out is, unless you're doing a nearby Pulsar that does not need dedispersion, if you're doing one further away, then Riptide needs a dedispersed file in either the Presto or SIGPROC format. Well, with Windows 10 or 11, you can install WSL. That's the Windows subsystem for Linux. That's what Microsoft calls their virtual Linux. So when you install WSL, you're just installing a virtual Linux under Windows, which is fine because I do the same thing here. I run Linux, but I have a virtual Windows. So it all works out. But when you install WSL, you can configure it with Ubuntu 18 or 20 or 22, your favorite Ubuntu. Once you have Ubuntu on there, then it's much easier to install and configure Presto or SIGPROC because either one of these packages needs a boatload of libraries, all the old Fortran libraries, FFTW, all those things. And they need the GNU Auto tools. But if you use a package manager here in Linux, it'll do most of that work for you. Or if you want to stick with Windows, Peter East, and there's others on GitHub, you can modify an existing code that does the dedispersion. The modification would be to simply put it in the format that Riptide is expecting, and the format is simply the data points. So it's a simple little binary file. In the summary of the results we looked at, so here's the source, Pulsar. I was interested in the dispersion measure and comparing it with distance. And, in some cases we had, well, here's a very large dispersion measure, but the distance wasn't that great. Well, that's because you're looking down, the plane of the Milky Way. Here we have a very large distance, 49 kiloparsecs. Well, that's when we're looking outside the Milky Way into the large cloud of Magellan. The dispersion measure was not the highest. It's high at 100, but not the highest we have. Here's the width, the half peak full, the W50 in milliseconds of the width of the pulse, the duty cycle in percent. And this data is from the ATNF. It's the flux at 1400. So even though a lot of these are at 1291, I use the 1400 flux just to help plan the how long to do a collection for. So here's the topocentric period produced by Presto. Here's the topocentric period produced by Riptide. These were the same values I was putting on the displays earlier. This is the difference, the absolute value of the difference, and it's very small, from a few nanoseconds to a few microseconds, and that's within the capability of our equipment. I don't know that we can do better than that, than some of these. These were the SNRs that I'd put on the previous charts, and I just use UTC for file ID. So a couple of these I denoted. These were when Riptide still worked, but Presto had failed, and I kind of noticed it was around 3 when the FFT SNR was below 3, then Presto really wasn't acceptable, whereas you could still see something in Riptide. I did have some other ones I tried, these 2 pulsars on data that we collected. Both algorithms failed on that. SNR was quite low, so there was nothing in those. Both algorithms are free. They're professionally developed and maintained. Presto is very well established. It's been around, I think, about 20 years. It's discovered many new pulsars. It was designed to discover binary millisecond pulsars. So it was designed to work on very fast pulsars. It works very good on that. That's what it was designed for. So we're really not using it for what it was designed for, yet it still does the job for us. And it was designed for higher SNR at the big observatories. A con, well, Presto and Tempo are a boatload. When you start downloading those, keep notes. It took some time to do all that, but once you get it, there's a tutorial you can go through and start getting the hang of Presto. Riptide is much simpler. It's Python interface, and under the hood, it's all C. It's better on long period pulsars. And so the asterisk, this is a very recent result here. This was just published last month. So the long list of authors included Morello, who was the author of Riptide. They did a study at GMRT, which is the giant meter wave radio telescope in India. I think it's like 30 dishes. Each dish is 45 meters. And in this case, Presto had already done a survey of the data. Presto had discovered 43 new pulsars in that survey. And so what they did with Riptide, and it's a very detailed result with Riptide, they went and reprocessed the same data. Riptide found the same 43 pulsars and two new ones. It found 2 slower pulsars, and that's what they've been finding. Is they've done the same thing with Arecibo data. They've gone back and reprocessed Arecibo data, and Riptide will find some of the slower pulsars that Presto had missed. Well, a pulsar is a pulsar, whether it's fast or slow. It's part of the life cycle of the pulsar. So they're actually using Riptide to fill in more data on the life cycle of pulsars. They're finding more of the slower ones and doing more studies on those. And as I said, the runtime is equivalent. You get about the same runtime as Presto. The con, well, it's a new implementation, so it may have some bugs in it. I didn't find any. The match in the literature, it says the match filter works best on single peak pulsars. Roughly 80% of the pulsars are single peaked, and so the other 20% have a more complex peak where you have multiple Gaussians. But what I found was the match filter worked fine on the 2 examples of double peaks that I had here, so that seemed to work. And then the other con is it needs the external dedispersion tool for the pipeline, the data pipeline that we have. Just some use cases. You know, I think it's great for, at least, you know, for me, I'm still relatively new using Presto and relatively new processing this very weak, very low SNR data. I like having extra confirmation. So Riptide gives independent confirmation of these low SNR pulsars. And sometimes when you run Presto, the results are ambiguous. And at least to me, it's not obvious if the pulse is absent or if the folding parameters are wrong or something else is wrong. And so you can spend a lot of time iterating Presto, or I can just go run Riptide to screen the data, because Riptide will come back and say if there's a pulse in there at all. Or it could be an alternative to Presto. If Presto is something you don't want to deal with, then I think Riptide makes a good alternative to it. And that's my last chart. And in the proceedings, there is this bibliography, the papers that I've referenced, the other presentations, and then the websites where you can get the data and the codes. So any other questions?
I have a couple of questions, if I may.
Yeah.
When you were doing the Presto processing and the Riptide processing, my understanding is that in both cases you let the algorithm look for a period. Is that correct?
So when I run Presto, I can either run it manually from the command line, in which case I tell it the period to use, or what I do, it's all scripted now, is I generate a .par file from ATNF, and it automatically, it has the barycentric period in that par file, and it converts it to the topocentric period for my location. And that's the same way that Greenbank generates its Presto files. It uses a .par file. When I run
I was just wondering, you can run Presto either with letting it search for a period, or just define the period from the par file. But so you have to use the parameter no search if you don't want to search. And I got the impression that you in any case you let the Presto search. Is that correct?
I usually I tell it no DM search and no period search and those things. So I turn off the searches. Sometimes if I'm not getting good results, I will open that up and let it search around. When I'm running Riptide, it's different. I give it a narrow bounding box around the known period. You know, the known period in this case is I start with the barycentric period, but I give it a wide enough band around it that it'll find the total period.
Yeah, I think that's one of the limitations also of Presto, that you can't give it a narrow range of periods to search. Okay. Another, just more a comment on the B2020 plus 28. This you have showed the example where only during part of the observation something was visible. The B2020 plus 28 is an absolute extreme example of scintillation. We have cases when we just don't see it, and we have cases when it's stronger than B0329. So it's sometimes it's just blowing your dish out of the water, as strong as it is, and sometimes it's just gone. So it's no surprise what you're getting, that it comes up during the observation. So you may try it a couple of more times. You will be surprised that sometimes it's very, very strong.
Okay, that's good to know because, like I said, it's if you've been down to Haswell, you realize, oh, it's a long drive down there, and so we get there, we get everything working, and then we do our data collects, and sometimes it's we get back home when we're processing the data, but yeah, when I collected that one, I thought, what in the world? There's nothing there, and then finally at the end, I didn't realize it had that such severe scintillation. That's good to know. I'll keep that in mind because it makes you wonder if something's wrong with your equipment or something's going on in the sky.
Yeah, we had exactly that we had a strong signal, and a few days later it was just gone, and we were just saying, okay, there must be something wrong with our equipment.
Mhm.
Just a final question: have you done any comparison, or have you ever tried to use PS Archive?
So I did. I installed those tools, and as I was installing them, and I was running some of their utilities, I realized I really wanted to use a second machine because all the environment variables and all the software packages I wanted to use, I actually kind of want to use a different machine to set up PS Archive with Tempo 2 and keep another machine for Tempo 1. But so I really have not used those tools enough.
Yeah, okay. PS Archive, in my experience, is a pain to install.
You might consider using virtual environments, and that way you can create different situations for each on the same computer.
Yeah, I can do that. There is a slight performance hit when you do the virtual.
Right.
I got some questions when you can.
Can you comment on the impact of the data gathering time length? Because it appears that gathering more data dramatically improves the signal to noise ratio.
Oh yes, absolutely. And that's the trade-off is how long do we collect data for? We can't, it's hard to go down there and let data, run data for 10 hours. If you do a 10-hour collect on these weak pulsars, you will have more data to fold and you'll get a stronger SNR. But for us, it's a trade-off is how long do you want to spend on one pulsar before you go to the next one?
Can you copy me, Jim and Brian?
I'm sorry, can you repeat that?
Can you hear me? It's Jim and Brian. Hello.
Go, James. We can hear you.
Okay. I've watched this with great interest. This is a wonderful presentation. Done some wonderful work. I wrote something similar to Riptide and published papers about it in the journal from about 2001 to 2010. You might want to look at that. Now, this one did not have all the features of some of the other ones, but it was a completely homegrown system. It appears we detected a number of pulsars, but the project was not well received or well supported by SARA's membership at the time, and so I stopped publishing papers on it. But you might want to look at the data at what was published and do a comparison. I would love to hear your thoughts on that. Thank you.
Okay, great. Yeah, I will go look at that.
Okay, any more questions?
I got a question.
Go ahead. Are you Peter?
Peter, you're on mute.
I'm on mute. Okay, can you hear me now?
Yeah, go ahead.
Yeah, good. Super presentation, Dan. I've got just one question. When you ran Presto, you used the incoherent harmonic summing to calculate the SNR. Did you look at the best profile and calculate the SNR that Presto produced for that?
So yes, actually, I'm lazy and I didn't want to code up my own, so I'm using I0NNA best profile to do the SNR.
Right. But you use that from the incoherent harmonic summing, the FFT.
Yes.
Is the FFT SNR rather than the prep fold standard folding SNR?
Yes.
Well, the prep fold standard folding SNR should be the same as the FFA SNR.
So I don't think they'll be the same because they're measured completely differently. They'll trend up and down the same, but they won't. You can't compare them numerically.
Right. I know the FFT SNR is always a lot worse
Mhm.
because the incoherent harmonic summing, you don't get the full energy in the folding algorithm, in the frequency folding algorithm. But the standard prep fold best profile is the standard folding algorithm, and the FFA should also be equivalent to the standard folding algorithm. So they should both be pretty similar.
So I'm going to go back and look at that because that best profile is just that ASCII text file. I'll go back and look at that. That's interesting.
But it's a great presentation and it's a super bit of work. A very excellent investigating job you've done there.
All right, thanks.
Hey Dan, I have a question. This is Mario. Do you hear me?
Yes.
Yes, first of all, I'm very happy that you are using both murmur and best profile analyzer. I'm very glad to hear that. The question is, can you comment a little bit more on Riptide installation?
On the installation of Riptide?
Yes, yes.
If you're running Python 3, then all you do on the command line is, I mean, there's various ways of installing Python packages. You can use PyBombs or whatever you like, but pip is easy to install. Pip is a Python package manager. You just just say pip install Riptide FFA. So you have to be on internet, because if you have the internet connection, it'll go out and get all the libraries it needs.
So it's straightforward then, nothing fancy like Presto or SIGPROC.
No, just Python. It has C libraries in it, but they're compiled libraries, no run.
Okay, thank you.
Mm-hmm.
And Dan, Mario had a question yesterday about how to install Murmur on a Linux machine. It looks like you solved that problem.
Well, his question was how to install the new one where he did all the graphs and plots. Okay. And I haven't tried that one. That might not work under Linux because of all the plotting and graphing. Murmur is a simpler package. It runs under Wine. So I just use the Wine emulator to run Murmur under Linux. I don't know if the other package would run.
No, actually, no, don't. I mean, actually, just for Windows, no, not Linux.
Great. All right. Well, thank you, Dan. And it looks like all the people that you referenced are actually online today. So it's really nice to have everybody. Shows that the collaboration has resulted in the product you've been putting out over at DSES. So thank you very much. Excellent work.
Thanks.